Hello, people, and welcome back to another session. In this session, we'll be continuing our discussion from our previous session where we discussed about how to perform statistical inferencing for our coefficients in a simple linear regression model. In our previous session, we saw how to calculate the test statistic for an F test, and we also discussed that our F test will be conducted at 1 and n minus 2 degree of freedom. And in this session, we are going to take an example in R and we'll perform hypothesis testing for one example. Now, in the previous session, we spoke about PF and QF, the two functions in R that we'll be using, which are directly correlated or similar to P norm and Q norm and PT and QT for their respective tests. So if you look at PF and QF, PF takes the point and it gives you the area or the probability towards the left-hand side of the graph. So basically, this is the F value. PF gives the area to the left. And if you have been given the probability to the left, putting that probability into QF is going to give you the F value. So now that this concept we have already seen before in our other tests, what is different out here, as I already mentioned in my previous session, that Z test and T test can be one-sided or two-sided. F test is always one-sided. We'll see that in the example also. So our alternate hypothesis in case of statistical inferencing for correlation coefficients is that my slope is not equal to 0. Technically, if we would have done a t-test, which we'll be discussing in our next session, it would have been done as a double-sided t-test. But since this is f-test, we have to do it from the concept or from the perspective of one-sided test. So we'll take our students' data set that we have been using in all our examples. This has 31 rows and it has two variables, hours and score. In our previous session, we saw how to create a simple linear regression model for, for scores as the dependent variable and hours as the independent variable. So M is my model. And when I print M, I get intercept as 51.51 and slope as 5.012. So this is what we saw as our equation for simple linear regression model for the dataset that we have. So now we have our model in place. Now to get the values of my regression component and my residual component or the ANOVA table, there is a function in R called ANOVA. If you pass your model to the ANOVA function, this is going to return you your ANOVA table. Now you can clearly see over here, you have your residual component and your regression component or your component of the slope. This is your K value, which is the degree of freedom for my regression component. And this is my degree of freedom for residual component, which is 31 minus 2, 29, n minus k minus 1, or in SLR, it's n minus 2. This is my mean sum of squares. This is my F value. So the F statistic value in this case is 103.17. This is the value for test statistic. So your test statistic, you can directly get it from your ANOVA table, right? So you give the ANOVA function and your ANOVA function will return to you your F statistic value. Now you have your test statistic. Now you need to compare your test statistic with the critical F values, right? So let us suppose that I want to know whether there is a linear association between score and hours at alpha is equal to 0.05 or 95% confidence interval or 95% confidence level. How will I go about doing this? Again, as I mentioned to you before, this is my if this is my F critical value, and I have been given my alpha value is 0.05, since F test is always one-sided, this confidence level towards the left of F critical is going to be 95%. So this CL here is going to be 0.95. Now, how do I calculate my critical F value? You have been given the area towards the left of your critical point, and you need to find the critical value or the point value. So you need to use the R function QF. So QF, I will write 0.95. Now, my degrees of freedom, I need to put them in the order of k, comma, n minus k minus 1. Remember, if you change the order of degree of freedom, your answer is going to change. So when I said your F test will be conducted at 1, comma, n minus 2 degree of freedom, it is exactly in that order. Your answer will be different for F conducting your F test at 1, n minus 2, comma, 1 degree of freedom. Okay? Put 1, comma, 29. And you get your critical value as 4.18. So my test statistic is 103.17. My value or my critical F value is 4.18. My F statistic value in this case is actually much, much larger than my critical F value. So I can clearly surmise in this case that I have sufficient evidence to reject the null hypothesis, which states that there is no linear association between hours and score. This is a fundamental and a very basic example of statistical inferencing for our coefficients of simple linear regression. Also, if you can see over here, your p-value for this corresponding f value is extremely small, which also tells you that we have sufficient evidence against our null hypothesis. And at 0.05 alpha level, we can reject the null hypothesis. So this was a basic example using R programming to conduct statistical inferencing for our coefficients of simple linear regression model. In the next session, we'll begin with t-test, and we'll be also covering the conceptual aspect of it and the programming aspect of it. So thank you so much for watching this session. I'll see all of you all in the next session. Thank you.